Okay, so today we're going to talk about reduction of order. Hopefully this will be a little refreshing after doing mass and spring systems for a little bit. But what this is just another tactic of solving second order differential equations. So we have in front of us the normal setup. We have this differential equation here. The constants in front of the y prime and the y can be functions of x, as we said a long time ago. And then if we go ahead and solve this using what we know, we pop out c1y1 plus c2y2, which we know to be solutions to the homogeneous equation. And then we pop out our particular solution as well, which takes care of this term on the right-hand side. And so we know we need these solutions to entirely describe the set of solutions to this space. So the question is then, is if I give you just one of them, if I pick a y1, which solves the homogeneous differential equation, can you tell me all the other solutions? So if given y1 of x as a solution to the homogeneous differential equation, so I just set f of x is equal to 0, are you able to tell me the rest of the solutions? Can you tell me what y2 is going to be? And can you tell me what my particular solution is going to be? And it seems really far-fetched, right? How are we going to figure out what the other linearly independent solution is? And in particular, how are we going to figure out what y sub p is for this if we're only given the solution to the homogeneous question or differential equation? The answer is actually yes, and it's really cool. How do you do it? Well, you use reduction of order. And so what we're going to do is we're going to go through and do this process. We're going to reduce the order of the second differential equation to get it down to just a first order linear differential equation. And we know how to solve those. We use the integrating factor to solve those differential equations. So if you haven't heard of the integrating factor before, I would suggest you go back and watch the previous video on that, because we'll be using it in a little bit. But I think the textbook does not do a very good job of explaining this section. There are a lot of, I know they have to do all the terminology and stuff, but as a student, it's frustrating to see not a lot of example problems. So I think the best way to understand this topic is to just go through and learn it via example. So what we're going to do is we're just going to start with a differential equation, and we're going to start with one of its solutions. So we have y double prime minus 3 over x y prime plus 4 over x squared y is equal to 8x squared, and I just need x to be positive. So on an exam, a good way to know that you're supposed to use reduction of order is because you have non-constant coefficients here. So these are functions of x, and we haven't really been dealing with those all that often. And then the big telltale sign that you want to use reduction of order is that they give you one of the solutions already. So it'll read something like, find the general solution if one solution to the homogeneous differential equation is, and then they give you a function. In our case, it's going to be x squared. So we're going to take all they give us here, this first solution, and we're going to find the other ones. And what we have to do is we have to just do a trick here. So what we first have to do is say that our function y of x is equal to another function u of x times the function they gave us. So we're going to assume that our solution y is going to be some function times the one solution they gave us. So this will just be x squared times u of x. And so if y of x is indeed a solution, remember we're trying to find that it's a solution, then I can plug it in to my differential equation. And I should be able to have it satisfy it, right? So what we're going to do is we're going to plug y of x is equal to x squared times some other function u. We're going to literally plug it into the differential equation. So I'll copy it again, y double prime minus 3 over x y prime plus 4 over x squared y is 8x squared. And then we have to go through and we have to solve and see if anything will cancel out. So what we do is we just take the derivatives first because it's easy and it's not messy, and then we can plug them all in where they need to be. So with the chain rule, I have 2x times u of x plus x squared times u prime of x. And then if I take the derivative of that, I have a couple more chain rules. I have 2u of x plus 2x u prime of x plus 2x u prime of x. And then from the last, I have plus x squared u double prime. Okay, so that was just quick, but it helps me organize myself to do them first and then plug them in. So if I plug it into the differential equation, y double prime becomes x squared u double prime of x. And I'm in fact going to drop the subscript of x. Just remember that u is a function. Plus 4x u prime plus 2u. So again, that just came from this and that. And then I have minus 3 over x times y prime, which was 2xu plus x squared u prime. And then I have plus 4 over x squared times y, which is just x squared times u. And that should give me 8x squared. So what we do, we just expand all of this out. So there's a lot of algebra going on in this topic, but x squared u double prime plus 4x u prime plus 2u minus 6u plus, nope, minus 3xu prime plus 4u is equal to 8x squared. So just expanded everything out. And so what we can do is we can group the like terms. So I have just one u double prime term. My u prime terms are here and here, so I get plus x u prime. And then what happens, and this happens every time, and why I think it's beautiful, is we have the u terms cancel out. So my u terms will always cancel out. I like to go through and do this expansion out anyway because I like to make sure they cancel out, but they will. They will always cancel out. And so I get that just this is equal to 8x squared. And so what we have here, and you might not recognize it yet, but we actually got rid of one of the orders. We started out with a y double prime, a y prime, and a y. That's not supposed to go there. And a y, but the y is gone. There's no more just simple function. So we now have, and I'll write this out. First, so we can solve this using the integrating factor method. And just to make this even more clear, I'm going to do one more change of variables, and I don't want it to be confusing. So I'm going to write some new function of w. I'm just going to define it to be the derivative of u prime. And then w prime is if I just differentiate w. So I get u double prime. Okay, so this is just, this is for convenience. And it's just so you guys can also see this become first order a little bit better. So I now have x squared times w prime. So I just substituted that in. plus x times w, so again, substitute that in, is equal to 8x squared. And now if you go back to the last video where we talked about integrating factor, this looks exactly like what we started with. We just have a w prime and a w. So we've reduced the order. This is not second two derivatives anymore. It's just the first. And we can solve this pretty easily. So what do? We use the integrating factor method. So I have to get w prime with no coefficients. So I divide everything by x squared. And then I use the integrating factor. So I just call it IF. And that's e to the integral of 1 over x dx. So this looks scary, but it should look familiar. If this is the first time you're seeing something like this, you're in the wrong video. And this is e to the natural log of x, which we can simplify down and just becomes x. What we do with this integrating factor is we multiply this entire differential equation by it. So we have w prime times x plus 1 times w is equal to 8x. And then I'll go over this one more time briefly, is what you're supposed to do on this left-hand side is notice that this is a product rule. So we have here, we have a function and its derivative. And then we have a function and its derivative. And then we multiply the respective parts and add them together. So we do indeed have a product rule. And what is that product of? It's the derivative of x and w. And that's equal to 8x. Now what I can do is I can literally integrate this out. And so I have x times w is equal to the integral of 8x dx, which is 4x squared plus c. We'll call it c1. And in calculus A, B, BC, whatever, your high school teacher might have yelled at you if you didn't have this plus c on the end. It's more important now than ever. You need this plus c, and we'll see why you need that in a second. So please do not leave that out. What you do now is you just solve for w. So w then, you just divide everything by x. You get 4x plus c1 over x. Okay, and so what you've done is you've exhausted the process pretty much. Now what you have to do is you have to start working backwards. So we substituted something in for w, so we need to find what that is. And then we also had to do something to our u in the first place. So if you remember right here, we made these substitutions. So I'm going to use this one here. W of x was u prime of x. So if I want to figure out what u is, I need to integrate w. So u of x then becomes the integral of 4x plus c1 over x dx, which gives me 2x squared plus c1 times the natural log of x plus c2. Again, please bring this with you. You need the c2. All right, so there's a u. And then the last thing that we need to do is we know that we said y of x has to be equal to x squared times our new function u. So we just multiply it by x squared. So y of x is equal to 2x to the fourth plus c1 x squared log of x plus c2 x squared. And believe it or not, we're done. This is our general solution to the differential equation they gave us. So if you go all the way back up, this was our solution, a pretty nasty equation, honestly. And we were able to solve it using reduction of order, and actually in a pretty simple process. So what I like to do now, if I have the time on exams, is I like to stick this back in. I like to plug this into y double prime minus 3 over x y prime plus 4 over x squared y, and make sure it does indeed give me 8x squared. So that's what I would do if I had the time. I've done it on my own, and I can confirm that it matches, so it might be a good exercise for you to do. And yeah, this was pretty much what you have to be doing here. So just as a little recap, the key here is defining this u of x times y1 of x. The thing you need to recognize is that your u's will cancel out, and so you have reduced your order. If you like to, you can make the substitution. I always think it's easy because you can work with better variables, and then at the very end you just have to make the simple integration here. That always works for me pretty well. And then at the very end, you just have to multiply through, and you're done. So this is just another tool we can add to the toolkit of solving second-order linear differential equations.